Hold on tight, folks. This is the breakthrough in anti-gravity. Scientists want to reverse gravity and say we can build a real anti-gravity machine and completely turn physics on its head. Literally.
Today is going to be really wild. Let's go, guys.
Just a quick note up front, if you don't want to miss any more science news, go ahead and subscribe to the channel right now. It's free and it really helps me out.
And for those who've already subscribed, a thumbs up helps the video immensely. 5,000 likes should be enough to appease the YouTube algorithm. Thanks, guys. Right, let's move on to gravity. It's the only one of the four fundamental forces of the universe that we still haven't been able to reconcile with quantum physics.
Electromagnetism, the strong nuclear force, and the weak nuclear force. All three can be described beautifully using quantum mechanics. Gravity, however, stubbornly resists this. Einstein describes it as a gentle curvature of space-time. We're all familiar with depictions like these of celestial bodies warping the space-time fabric, but to this day we still don't know whether tiny quantum particles might be hiding behind this curvature.
Is there a gravity particle or graviton? That is precisely one of the greatest unsolved mysteries of modern physics. And a team led by physicist Pablo Saldanha from Brazil, together with Oxford researchers Chiara Maletto and Vlatko Vedral, has now published an absolutely crazy plan that could revolutionize physics. And it's all about anti-gravity. I can already see some puzzled looks. How does gravity relate to anti-gravity? Well, about the same way pasta relates to antipasti. Complete nonsense, I'm just hungry.
The probe is pulled by gravity from two directions at the same time because the other particle is, in a sense, in two places at once. If one then selects very specific measurement results, these two effects can interfere in such a way that it suddenly appears as if the probe is not being attracted but pushed away. And it is precisely this surprising effect that the researchers call anti-gravity. Vlatko Vedral, one of the participating physicists from Oxford, explains the principle as follows. In the end, post-selection is crucial because only if you pick out the correct measurement result do you actually get anti-gravity. On average, across all possible results, gravity remains classically attractive.
By the way, this Vlatko Vedral is a pretty impressive scientist. I watched several interviews with him for my research, and he explains the realm of quantum physics with incredible passion. Take a look here.
And I think it's simply the consistency that if you have a bona fide quantum system, like you know that an atom or an electron is in two places at the same time, you've really put it in a superposition of two places. It now generates an electromagnetic field of a certain kind. And the question is, how do I describe this now? If really the electron is fully quantum mechanical, but you don't allow the field to be quantum mechanical, right, it seems that there is a fundamental inconsistency there. And I think Heisenberg explored this quite a lot in the early days to argue that actually if you really could couple a classical system like that to a genuine quantum mechanical, you'd be violating his uncertainty principle. Because basically you could now squeeze this quantum information into something that definitely is in one state or another, right, which would obviously contradict the basic laws, even of the quantum mechanical system, right, that you originally assumed was quantum mechanical. So it seems to me if you take a massive object, and we can argue how massive this object needs to be to make a significant effect gravitationally, but if you put a mass in a superposition of two different places, then you are really faced, and I think Feynman said this a long time ago, you are really faced with a very stark choice there if you do not allow gravity to also be quantum mechanical and to respond to the mass in each of these, right, places simultaneously.
Right. Fine, but that thing about post-selection sounds like cheating, doesn't it? I'm just fishing out the results so that my premise fits. But it isn't. This is by no means a sleight of hand or a mere mathematical trick. Because if gravity were purely classical, that is, as Einstein describes it, then such a repulsion could never arise, no matter how often or how skillfully you measure. Only because gravity can interfere with itself quantum mechanically here does this repulsion become possible at all. And that is precisely why the actual observation of this effect in the laboratory would be genuine proof that gravity possesses a quantum property. I know it all seems totally like science fiction, like it was stolen straight from the latest Hollywood movie. How many movies have I already seen in which the propulsion system that allows spaceships to travel light years is simply explained by anti-gravity?
However, none of this is as far-fetched as one might initially suppose. This is because the researchers also provide very concrete suggestions in their paper as to what such an experiment would actually have to look like. As source particles, they propose tiny nanodiamonds containing a single nitrogen vacancy defect, known as an NV center for short. Using magnetic fields, such nanodiamonds can be precisely placed in a superposition of two positions that are several hundred micrometers apart. Clouds of cesium atoms, as used in experiments with Bose-Einstein condensates, could serve as the probe. So yes, if you happen to have a few nanodiamonds and some cesium lying around in a drawer at home, maybe even a little duct tape, why not build a nice little anti-gravity machine tonight? If in the end something repels something else and there's a big bang, then it worked.
To make the tiny effect measurable at all, the researchers use a clever trick called weak value amplification. Simply put, this allows the magnitude of the measured repulsion to be amplified by several orders of magnitude.
However, this comes at the cost of the desired measurement result occurring with decreasing frequency. It's a classic trade-off between signal strength on the one hand and probability of success on the other, a phenomenon familiar from many areas of quantum optics. In their study, the authors provide very specific calculations of the masses and distances required to actually carry out such an experiment. And even though the required masses are currently still somewhat larger than in previous proposals for so-called gravitationally induced entanglement, the new approach has a decisive advantage. Only a single particle needs to be placed in a superposition, not two at once. And in the end, there's no need to measure complicated quantum correlations between the particles, just how the probe's momentum has changed. This makes the experiment significantly easier to carry out in comparison. Vlatko Vedrel himself is very confident and says, fortunately, several world-leading quantum research groups are working flat out to carry out these experiments, and I'm optimistic that we'll be able to present conclusive results in the early 2030s. So we're on the verge of solving one of physics' greatest mysteries, and on top of that, could develop a true sci-fi technology. But what's the point of all this? If the quantum nature of gravity is confirmed, physicists could begin developing entirely new types of quantum computers that use gravity itself as a computational resource. Some researchers even speculate that, in the distant future, black holes, which store more information per unit volume than any other known object in the universe, could be used as the ultimate quantum computers. This idea is also referred to as a matryoshka brain. In this scenario, a star or black hole would be surrounded by several nested shells consisting of countless computers that use nearly all of its energy for computation. This is similar to an extremely advanced Dyson sphere. Theoretically, such a machine could perform unimaginably complex simulations. Potentially, it could be used to simulate entire universes. Realistically speaking, however, we are still in a very early stage of research here, far from any functioning prototype, and unfortunately, the practical implementation won't be quite as simple as it sounds in theory. The researchers themselves explicitly point out in their study that the quantum effect they are looking for must be clearly distinguished from other, much more mundane sources of interference. One such candidate, for example, is the Casimir-Polder force, a tiny but entirely classical attraction between objects that arises from quantum fluctuations in the electromagnetic field and has nothing to do with gravity. At distances in the micrometer range, this force could easily compete with the signal they're looking for, but even so, the study shows just how creative physicists have become in their quest to solve one of the last great mysteries of our universe.
And when you listen to Vlatko Vedrel, well, then the optimism is truly contagious.
And it's fully consistent. That's what's interesting. It is a mind-blowing picture of reality, but it is fully consistent. No matter what you read anywhere where people say quantum mechanics is wrong, it can't be right, and so on, it can be right. Logically, there's nothing wrong. Of course, it can fail experimentally, and that's going to give us a lot of food for thought. And what I'm most excited about, and this is my prediction. Of course, people keep making predictions, and we all do, and we are all proven wrong frequently. But I think by the end of this decade, we're going to have some new physics. The least will be this falsification of general relativity and the realization that gravity itself ought to be quantum, at least at some level. And this is hugely exciting for us physicists. The technology has managed to reach this level. For 100 years, we've had these two theories
and we're all probably pretty bored with all of this. We'd like some novelty. And I'm really predicting that by the end of the decade, we will have these experiments, and they'll be informing us what to do there. You might get a new theory, maybe quantum gravity, maybe going beyond that, maybe telling us nature is even weirder than all this. It's all possible.
And even if it should turn out in the end that gravity remains completely classical after all, we will learn a great deal about the foundation of our reality through such experiments. For me personally, it feels incredible that we are now seriously discussing blueprints for anti-gravity machines, even if they currently look more like laboratory experiments than flying cars. But who knows, a little more research here and a few more experiments there, and bam, we'll be building the Matryoshka brain in space. I will keep you updated on that. So feel free to subscribe to the channel now, and don't forget to hit the like button so we can reach 5,000 likes. As for such quantum experiments, let's stay tuned to see what the 2030s have in store for us.
In contrast, the event we're discussing now is much more tangible and, in the truest sense of the word, earth-shattering. Our moon was just struck by a mysterious non-natural object, and the resulting explosion was gigantic. What's behind this? And where did this object really come from? You'll find out that and much more in the video in the top right corner. Be sure to check it out for the original footage. It's very, very exciting. As always, in the bottom right corner, you'll find another topic related to science and space. Otherwise, I'd say, see you in the next video. Take care, everyone.